Thanks, everybody. So I'm just going to introduce the whole scope of the lecture, and then let some of the students talk first, and I'll follow. And then finally, we'll have our guests from Ecuador talking last. And before I start, I got to make sure they're in the room. So give us 1 second for that. Oh, they're in. Hi, Beth.
Wait, Jonas, is Lucas in? Is
what?
Lucas in? Lucas is in.
Hey, Jonas. I can see you and hear you.
Nice.
Okay, good. Everything is working.
Okay.
All right, so. Thank you, Patrick, for the introduction. So we're going to have Lucy, Adriana, and Sarah Yu each present some work. Then I'm going to cover the kind of MassBoo research, and then Regeneration Field Institute. Beth is going to present for about 10 minutes on the summer programs, and then I'll talk a little bit more about some other on-campus opportunities, and then we'll have a few minutes for Q&A, and then following we'll be in the lobby if there's more questions and we run out of time. Thanks. So please, Lucy, come on up.
Okay. What is this?
Hello. Hi guys. Can you hear me? Yeah? Okay, cool. I'm Lucy. I'm a 5th-year architecture student here at Virginia Tech. And last summer I had the opportunity to travel to Ecuador and to do an internship with Regeneration Field Institute, which we'll talk a little bit more about. But yeah, so I just want to give you a quick overview of my experience there. I was in Ecuador for 5 weeks, and so Ecuador is, as a country, is divided into kind of 3 climate regions. There's the Amazon region, which is the tropical rainforest. There's the Andes in the very middle of the country, and then there's the coastal region. And so it's a very diverse country. They have very different ecosystems and climates. And so the really cool thing about the program I did, I got to start out in the Amazon region in Tena and do the Virginia Tech kind of travel abroad program, which you guys all have the opportunity to do this summer if you're interested. So I'll let Adriana and Sarah kind of talk about that a little bit more. But after that program was over, I got to travel back to Quito and then go to Chelme, Ecuador, which is in the coastal region, and that's where Regeneration Field Institute has their headquarters. And so I got to live on this really cool bamboo farm, and I'll show you if you want to go to the next slide. So I got to work here in this amazing bamboo building, and my task as an intern was to take the bamboo panels that Jonas is developing and figure out how to make that into a building. And so it was kind of challenging because this is a brand new material that's never been used in construction of this scale before. And so I had to look at kind of precedent materials, thinking about like CLT, stick-built construction, and learn how to apply those tools and those ways of building into a new material. And so I worked with local architects from Ecuador and also some engineers, and so it was a really cool interdisciplinary process. But I came up with this proposal for kind of a modular system, and so it's a really simple kit of parts system where there's one size for the floor panel. It's an 8x12 floor panel, an 8x9 wall panel, and then there's a wall panel with a door, a singular door, and then a window. And that's the whole kit of parts with the bamboo beams for the roof. So up there you can kind of see they're pretty small, but some floor plans that I came up with for 3-bedroom, 2-bathroom units that could be easily replicated, and then just putting together some renders and stuff. And so Saryu and Adriana have developed this research more and furthered the design, so I'll let them talk to you guys about that.
Hi everyone, I'm Saryu. I'm a 3rd-year architecture student at Virginia Tech. Adriana, Lucy, and I, we started off with RFI as on-campus interns a little bit more than a year ago. I currently work as the lead campus intern, and I also work with Adriana and Jonas to continue Lucy's research. We all went to Ecuador last May, and it was an amazing experience, and we learned a lot. We were able to work with the students from ICIUM University to structurally test bamboo And also we learned about their own architecture program, which was really interesting. We were also immersed into the Ecuadorian culture. So we learned about their local construction processes. We toured some architecture firms, and we went on a lot of site visits. The Virginia Tech program is unique because we're in Tena, which is in the Amazon. So outside of research time, we were also able to do a lot of fun activities like hike in the Amazon and also go to waterfalls, which was really amazing. The program gave me a new perspective on architecture and how to approach design. And if you're interested, we're also going back to Ecuador again this May. So if you want to learn more, please feel free to email me or come up and ask me questions after the lecture. You can also get 80 AXP hours for your architecture license if you're interested.
So some more on our trip is we did a lot of testing with these bamboo beams. They're lightly modified, which means we're only taking a small amount off of each. So from that testing we did in Ecuador, we kind of further developed the bamboo panels. So each of these panels has, these layers in it, and with those layers we go through and create these different pieces that we can just put in the housing units. So like Lucy said, they kind of all have specific uses. We'll have one panel with a door, one panel with a window unit, and those get put into our housing types. So Sariu and I have been continuing the research, and we developed 6 different housing unit types. So these are 1 to 4 bedroom units, and these all kind of use the same premise of the panel system. And our whole system is based on multiples of 4. So for the panels, you can kind of move them around, but they all fit within each other. And then those units, this is kind of one of them. This is the 4-bed, 1.5 bath unit. And this shows just kind of the housing unit as a whole and how we're further developing it. But from this point, we'll take it and go forward into developing the panels within each of these unit types, and then kind of looking at it from a climate standpoint and how we can kind of take the specific quantities in these panels and see how much that we're able to design with each individual one. But that's our research that we're continuing, and then we can pass it off to Jonas, who will go more in depth.
Good job. I don't need the mic, I don't think. Can you all hear me okay without the mic? Okay, good. So to begin with, I just wanted to acknowledge that there's probably at this point a few hundred students from architecture, industrial design, and S-Bio that have participated in the research, just from VT, and then around the world another probably 100 people have also touched the research in some way. We've been really kind of keen to learn from traditional bamboo systems, learn from engineered bamboo systems, and in that process have just met lots of people in lots of different groups. And so, the Biodesign Research Group kind of sits at the middle of that collaboration, but also in the College of Natural Resources, Dan Hyman, who's a structural engineer and a wood scientist, he's a collaborator. He has a bunch of kind of contacts, and then also RFI has become more and more of the key strategic partner. We also have a collaboration with Base Baha'i in the Philippines, but that's kind of slightly behind the kind of edge of the research. In Ecuador this summer, or I'm sorry, not this summer, just this last month, with the Polytechnic in Quito, with Diego Sosa, a structural engineer, we tested about 20 panels, and we actually was just on a call this morning about the kind of report, and we should have enough information from these early tests to then go to full-scale testing in Ecuador to get a building code kind of changed or made. You have to test full-scale structures, and actually the EPN lab is the place in the country this happens. So we're working with the right people, and I would guess within the next year or two, largely based on funding, we'll be making a full-scale, shake table test that's 2 stories tall, but probably the forces will be more like a 5-story test. So I also wanted to acknowledge some craftsmen, specifically James Wolf, the guy on the left. He's an expat that spends most of his time in Vietnam the last 20 years. He makes bikes, and he introduced me to just thinking about these bamboos that are more solid. And he was kind of showing off one of the 2 common species there. It's called Tre Gai in Vietnamese. Tre Gai and Tam Vong are the 2 common species there. And He's like, look, we can cut a 4x4 out of it. I remembered the image in my mind's eye on the right, and I conveniently forgot the one on the left where it didn't work, and then came back and said, oh, we're going to make CLT out of bamboo. And we've begun to do that, but that's been a slow and arduous process. So the basic part of this talk came from a talk I gave at the Architects League about a month and a half ago, and it sort of covers these topics: the kind of housing crisis, thoughts about materiality, the bamboo spectrum, as I've coined it, MassBoo as a kind of system, and then what we're trying to do to begin to scale this and how we think about scaling, a research project or a small enterprise into buildings. Why we're doing this is because, of course, there's a huge need for housing. 96,000 houses every day aren't built around the world that are needed. We know by 2050 something like 2 billion more households are needed. A lot of those are in the bamboo belt. The green kind of belt in the image on the left is the bamboo belt, and all of those numbers are cities that need lots of housing. So in my mind, this notion about materiality, where we kind of have these synthetic materials and these organic ones, and we think, oh, natural materials are the good ones and the synthetic ones are the bad ones. To me, it's really the wrong way to think about it. It's more about time. How long does it take for a material to occur? How long for it to biodegrade? What is the right length of time? How durable should a building be? And so what's remarkable about bamboo is that in less than 10 years, you can start with nothing and have full height mature bamboo, and then after that, every year new shoots shoot to full height. In 3 to 5 years, those shoots are ready for construction. And so this is a really big game changer, but it comes with lots of complexities and challenges that have yet to be overcome, and we are trying to help overcome them. That's the whole goal of the research, is to help bamboo scale from one-story construction, which is becoming more and more common. There's beautiful work all over the world, Hong Kong, Bali, and really good social work in the Philippines, Ecuador, Colombia, and other countries, but there's really little effort now that is from round bamboo or near round bamboo to scale bamboo into a mid-rise solution, much like the way we've seen 2x4 construction in the United States, take on that space between low-rise and CLT at high-rise. So why it's difficult is because bamboo has significant eccentricities. It's not round, it's not straight, it has nodes, it's semi-solid and semi-hollow, it has cracks, and there's lots of other kinds of unique challenges. It's, if timber is a natural material that is simple, bamboo is a natural material that's complex, and it's because you really can't break it down into a unit from a big chunk that is then very, very repeatable. So we make efforts to make it more repeatable, but it will never be repeatable in the same way that timber is or steel is or any other engineered material. So some of the work we've done is really to kind of analyze the material, whether that's through fabrication, like the image on the left, building 2 projects in the CID about 5 years ago, or on the 2 images on the right, where we're building scanners and we're analyzing and weighing material, trying to understand what is the range of variability within what is considered the product. So the product might be, nominally 2-inch bamboo. How much range is there within that 2-inch bucket, and how straight is that 2-inch bucket, and how much range of node spacing? These kinds of things become important to understand. And then we try to build cool and fun stuff. Ramtin Hagnazar, I'm not sure if he's here, but Ramtin has run the most recent project, that yellow structure that was built a couple years ago, which is in some ways about studying digital fabrication and computation. It's also about trying to see where biodesign might interfere or support that kind of work, and of course inspire all of you to kind of play with these materials, to know them better and differently. So the real kind of place that the MassBoo system fits in is in between this thing that I'm going to share in the next few slides that I would call a spectrum, the bamboo spectrum, which goes on the left-hand side from bamboo that's engineered into structures from round bamboo, to on the other side, on the right side, these structures that are from highly engineered bamboo, where it's turned into little tiny rectanguloids and then glued together. And until now, those have been thought about as 2 different territories, not really as a spectrum, but as distinct areas of research and work. And my argument is that the real innovations have to come from compromise at some place in between. I'm not sure what's happening there. don't think so. They all look like they're blank, but they're not. Oh, somebody just threw a bunch of slides in there. Okay. All right, sorry about that. I didn't know that we've been collaborating on one deck, so I guess somebody just added a bunch of slides. So this spectrum, I think could be seen as a very small area. And so that's how it's imaged here. On the left is a really kind of well-crafted structure. You can see that there's lots of articulated joinery, fish mouth joints, stacked and bolted bamboo, reinforced bamboo that has cement inside of it and has a wrapping around the outside from a pipe clamp. This is to make sure the bamboo doesn't split open. There's really careful placement of nodes at just above intersections, not at the intersection. You can't be too far from a node, so there's lots of choosing and selecting and tailoring involved in that kind of work. And then on the right-hand side, strand woven bamboo uses something like 40% resin, gets really high recovery, but then there's tons of glue in it. And then if you look at these other bamboos, these are laminated bamboo, they use something like 20% of the stock, and you'll see in a minute why that is and how that works. And so I'm interested in this territory in between, which I then think is really, really large. And I think it's large, but I think the work we're doing probably sits right about here. So, much to the left, not to the center or to the right, but, within this boundless spectrum that I hope to encourage other researchers and other students of design, construction, architecture, and material research to really begin to examine other ways to take material apart and put it back together. So for us, the first kind of step is to think about bamboo as a unit that can be made semi-regular. So it can have up to 2 sides that are tooled, sometimes even 3, but most often 2. And when we do that in really solid species, we stay in the wall all the time. In these more hollow species, we don't. And so parallel lightly modified bamboo is shown on the left. And you can see here we've cut through, here we haven't, here we have. And this is what we just tested, and the panels all behaved pretty well because in the LMB that is parallel, 2 parallel sides running the whole length, we're cross-laminating. So when you cross-laminate, you pick up all the edges anyway. On the other hand, we also make what's called taper laminated bamboo, and this can be infinitely long, probably 6, 8, 10 meters will probably still work. That's because we're following the outside wall of the bamboo. So if the bamboo in any orientation is straight enough, we can make it flat on 2 sides, but those 2 sides are kind of converging together. In cross-section, it's flat and parallel, but in elevation of that long linear element, you're converging to, eventually to a point which we never reach. You think it's more of the same problem?
Yeah.
How did so many slides get added? Wow. All right, so to talk a little bit more about what the modification does. So when you modify bamboo, the first thought would be, oh, well, I guess I'm just going to leave it in the other mode. So if you see the image on the left, if you take a piece of bamboo that's around 9 centimeters in diameter, and you take a piece that's maybe 10 and a quarter centimeters in diameter, and you make it flat on 2 sides, whether you cut through the wall or not, it turns out that the one on the left is stiffer. And bamboo's biggest problem as a building material is not its strength, it's its stiffness. So this modification, you lose, if you did it in a pretty straight piece, you lose maybe 5% or 10% at the most. If it gets to be more crooked and you're cutting off more, maybe 15%. But when you lose 15%, you're not losing 50% of its capacity, it's just the biomass. And the biomass could be used as energy, or when those cuts are big enough, in a secondary process within the panels, or even for other products altogether. So the argument we're making is that actually we're fortifying bamboo by making this transition. We're giving it unitization, and we're giving it more stiffness. Also, if you look at the laminated bamboo, it uses every other cut out of one of the 6 meter or other length pieces from a standing bamboo. We're able to get 4 cuts out of it. So there's a huge increase in possible throughput. And this is why bamboo has 2 problems. It's not regular, and it's not efficient. And we're trying to tackle both of those with this system. So on campus, we've made, maybe 15 or 20 different small test panels over the years. And then we've also made, an installation, which you'll see in the other room. And this was really made for two reasons. One is to kind of broadcast this idea. The other was to experiment with joinery. So actually, each one of these panels is joined together in a different way, or has its orientation of skin made in a different way. So we try to make these these things that have aesthetic possibilities as kind of sculptural objects, but also that are testing the kind of technical qualities of the research. This was done finished maybe 4 years ago. To get into a little bit of the kind of taxonomy of the panel, the core we've seen so far, if you're gonna make a 3-layer panel, runs the long way through the center. It can be as porous as maybe 4 columns over 8 feet of length, or it could be as dense as 9 columns over 4 feet of length. So we really have a lot of range, and we're not really quite sure for walls yet, given buckling and in-plane shear, how many core elements will be needed. And then for a wall, we think we're gonna run the lath at 90 degrees, but for floors, we're gonna run the lath layers at 2 opposing 45 degrees. And so on the left, you can see a series of other experiments, some with woven bamboo mats from Vietnam, from Colombian Guadua bamboo, some just trying different orientations. We really didn't know what would work. The science of composite materials, of stress skins, would suggest that maybe this would have worked really well, but because of rolling shear, it didn't. So it turns out that this is really the best configuration, these two right here. Here you're seeing really solid bamboo as the outer layers. In Latin America and the Philippines, we don't have that species. It's in Vietnam. And so we're using bamboo that's unrolled into a kind of mat. And you'll see images of that later in the talk. Also, to kind of explain that thing about the taper a little bit more, so we take the big end and the small end, and we kind of flip heads and tails and laminate a rectangle out of 2 pieces that are tapered. So we wind up with a building unit that is parallel, that has these kind of normal unitized conditions, even though the material it started from doesn't really embody those characteristics. And you can see here how wall thickness has a huge impact on the amount of fall off. So when you have a much more hollow material, that cut takes away a lot more, and when it's much thicker and more solid, it takes away much less. Also, another way we're going to utilize more bamboo is by making the ingredients of any one panel what they need to be. Sometimes you just need filler pieces. You don't necessarily need a whole lot of stiffness from them. So you might use really dense pieces on edges or in some core moments, but then in between, less dense pieces. Or you might think, I wonder if every floor of the building needs to have the same thickness. The floors that are public might have to be thicker or stiffer. And then even the walls on the 5th floor, do they have to be as dense as on the 1st floor? These are questions that we ask with steel sizing, but probably not as much with wood sizing. But with bamboo, I think it'll be important to ask these questions. So we've done some testing before this last month. We've done some over the years, mostly at Dan Hyman's lab. Dr. Hyman's lab is in Brooks Center. And the most high-performing floor panels could span the 12 feet with a 1/2 inch of deflection, which is allowable for residential construction most places. And in total bending, they could bend 6 inches before they failed, with a 12,000-pound load in the best cases. In the worst cases, with other permutations like putting the core vertically in a very short panel, they only took like around 2,000 or 3,000 pounds to break. The beams are much newer and a more mature kind of development. They started later, so we had more experience. And in like 10 days on this trip that we took last summer, it was the second attempt at this. I'd been to Iquium for 2 days the summer before and tried something similar just with a hand power plane, but without a fixture. And it kind of looked like it would work, so we then invested a little more energy in it this past summer. And these beams are 1.65 times stiffer than a bolted beam. So they take up less vertical space in the kind of floor to ceiling space. They cost less to make because the glue is way less expensive than the galvanized threaded rod. And they also have a smaller environmental footprint. And then on top of that, they also load on a truck and make a flat floor much more easily than you would have a bumpy bamboo. So we've made some usually on a farm or in a factory setting, or on a campus setting, some experiments that are living experiments. So the first summer we took a group there. We built with the wrong tools, the wrong glue. We built the floor of this little cabin. In the Philippines, the Quine Collective, which is an architecture and bamboo material company, built their office using these panels for the floor. And we've started to experiment with, is it going to be cement? Is it going to be biolime or some other skin that gives it the waterproofing and sun protection needed to make a durable building? Incidentally, we don't think we need the cement like you would use in wattle or daub, or what's called bahareke, which is the traditional bamboo housing system. We don't really need it for in-plane shear, but we do need it for sealing up the building. We've also played around with lots of other connections. I think that much like IKEA furniture that's made from particle board, on the one hand, it's like a really crappy material. It's porous and it can break easily. It's also really genius and really utilizes resources in a very different way than hardwood furniture would. And so we think that probably if we're going to have to grab the panels on the inside, not grabbing the edge is really important. And so we've been playing around with different ways to hack tools, making kind of drill presses that are made from a hand drill and a jig, or taking a chainsaw and making it into a mortising machine to make these different kinds of steel plate connections or pipe connections or splices or butt joints that are then reinforced with a wood block to create a denser place of attachment. I think Lucy covered the work she did really well, which is really excellent work, and we're really happy to have been able to be part of that process. And just to say that we've arrived at like maybe somewhere between 5 and 10 unique product types to make unitized, repeatable housing. Now we have to figure out whether it's cost effective, and we have to figure out whether the life cycle assessment really works out the way we expect it to, but I'll talk more about that in a minute. We've been developing really accessible tools. So like the first presses we made are just threaded rod and plywood and some 2x4 teak, which ironically is a really cheap wood in Ecuador. And using PVA glue, and now we're using Gorilla Glue, which many of us brought in our backpacks on the last trip because it's difficult to get other chemistries there. In the Philippines, I just brought a motor off of an old saw and built another machine there. And in Ecuador, the same summer, like I said, about a year and a half ago, I brought a motor, a fan motor, and just built a whole machine from scratch. And this is an ongoing kind of development. We're trying to invest as little as possible, both because we have very small budgets for this kind of research, but also because we want to use a distributed manufacturing model, a micro-factory-like model, where you might have, in every town or city, maybe there's a startup that's making housing, not one big mega factory that costs billions to occupy, and then also costs the economy, few people with all the, reap all the rewards. So the goal is to kind of democratize that as well. And we're kind of to the next level where we're trying to like slightly industrialize the machines, and this is what we'll hopefully build in the next couple months. We just won the Brunner grant from the Architects League, which should pay to build these 2 machines this coming summer. This is a nice AI speculation. It's based on feeding it lots of academic research on life cycle assessment for bamboo, but it looks like if we go to 5 stories, we can offset the foundation and the stucco with how carbon sequestering bamboo is, both as a growing material, but also as a durable lockup of that carbon into a building. So this we have to prove still. We're working with Edwin Escala he's Colombian, but he's faculty in Switzerland, and he's an expert in life cycle. So we're gonna work in this next year to really prove whether this hunch from ChatGPT is accurate or not. By the way, that's Lucas, and that's the warehouse they just built to pursue the MassBoo project at the farm. And now we're going to introduce Beth to kind of continue the conversation. Beth, can you hear us?
Yeah, I do.
Okay, so I'll
pass it over to Lucas.
Oh, okay, great.
To start kind of introducing the MassBoo from the RFI perspective.
Great. And just, Lucas, just let me know when you want me to go to the next slide.
Okay, yeah, I'll just talk on this. Is it the first one, Beth? Here?
Yeah, this is the first one.
Yeah. Yes, hi everybody. Could you turn the camera around for a second also? Jonas, I love looking at you.
That's not that easy to do, but I'll try.
I just was curious how the turnout is, how everybody. So, just to share briefly about our interest in the MassBlue collaboration. We started building with bamboo in 2016 as a disaster relief project. There's a 7.8 magnitude earthquake that destroyed a lot of coastal Ecuador, and we had been leading an environmental education project at that time, and many of the students involved in our program lost their homes. A couple of the high schools, we had school gardens and greenhouse projects. The high schools were actually completely destroyed. And so we were looking for a affordable, seismic resistant material that was in line with our environmental mission that we had of our work, and that's how we came to work with bamboo. Because of the scarce resources that we had and the big need that existed during that disaster relief work, we were constantly attempting to optimize the building process of the houses we were making. So how do we frame them faster? How do we use cheaper materials for the walls? How do we complete as nice and durable a house as possible for people in this disaster relief scenario with sometimes just like $5,000 or $6,000? We would we put screens on the windows and bamboo slats, but not windows, for example, to save money. Or we got some donations of tile flooring, but we couldn't pay to install it, so we would just give it to people, and then eventually, little by little, they would install it and kind of finish their house. But for us, it was important that we got a roof, some sturdy walls, and a nice elevated foundation built that was going to be, and then we use good quality treated bamboo so that it would be resistant to fungus or other kind of insect attack. So we really did get more and more efficient. And over the years, people asked us to build regular commercial projects as well. Houses, some little ecotouristic projects. And mostly what we did over the years was just pass on that interest from people to builders in our group who were interested in taking on those contracts, because we were typically busy with other things. But I was involved in a lot of different building projects over the past 10 years. And with RFI, every group that comes can build a community project like the ones you see on the screen. And so I was always interested in, okay, how do we optimize use of this material better? How do we reduce waste in the construction process? How do we make it more design competitive in terms of the aesthetics that people are looking for in the construction market, in the housing market here in Ecuador? And sometimes those answers were hard to come up with. Those questions were hard to find answers for because, as Jonas has shared, bamboo is morphologically irregular. It's hard to have a perfect seam between a ceiling and a wall because it has curvature and flares out at the nodes. In horizontal bending, it's very flexible, and so you have to put like 4 bamboo sometimes to go in a horizontal beam just to have it be stiff enough. And that's inefficient and costly. It's hard to have a perfectly flat floor because also the bamboo is curved and it tapers, so you have to always shim the floors when you're putting on wooden floorboards, for example, because it's hard to have a perfect plane across an entire second story, for example, if your material tapers and is irregularly shaped. And so at first, when Jonas introduced MassBlue, I was skeptical that it was not going to be dimensionally stable after slicing the bamboo the way that we do. But as we experimented at our farm over the past close to 3 years now, we started to see that it is, in fact, quite dimensionally stable, and that by slicing the faces of it and then adhering these different lath layers or gluing them together in the case of the beams, what we can do is create a dimensionally uniform, reliable construction unit. And that ours, according to some preliminary results from this testing we just did, significantly more stiff than other types of bamboo building systems because of the composite action you gain by gluing different elements together. So we've been Jonas had it for much longer than we have, but since we've been supporting and involved over the past several years, we've been trying to get people to be as impressed and excited as we are about the mass booth. And sometimes it's been difficult because it's sort of a completely different kind of material, but I think what we just saw with Jonas's last visit and the work that we were doing together at the National Polytechnic University of Quito, like the best engineering lab for home construction, at least in the country. And we basically had all of the engineers sort of starting to raise their eyebrows and look around at each other and sort of nod and admit to us even that, yeah, hypothetically, these panels can, go up to 5 stories. And so that means a lot coming from the numbers people that they're starting to sort of feel the potential as much as we are. And for us involving students, the last thing I'll say is that for us involving students in this research is an amazing opportunity because that's totally in line with our mission as an organization, is to have meaningful research that we can advance with the participation of students, students as intellectual and labor support for the research itself, but also to hopefully inspire you guys in the process of doing this research and to understand that we need new types of material solutions for the future. We need sustainable supply chains for our structural materials. And the way that we do things now, sometimes it seems like it's set in stone, no pun intended, but it's really, there's a lot of amazing innovation that can happen with biogenic materials, and your guys' generation is going to be the one that needs to do that, and hopefully Mass Food can be this big example of helping to lead the way. I think we're just starting to get some exciting traction. So I just wanted to chime in from the side of RFI on that, and why we're interested and motivated to collaborate with Jonas and DT and you guys as students.
Thanks, Lucas.
Yeah, thanks, Lucas. And I'm going to share more about how you as BT students or researchers or faculty that are in the audience today, how you guys can get involved as well. So next slide, please. So a little bit of our history Lucas covered, but just to kind of summarize, we were born out of the earthquake that happened in coastal Ecuador in 2016, and we really want to look at both bamboo construction and land management as like a way to ecologically regenerate bioregions that have been degraded. And we began working with Professor Hauptman in 2022, I think is when we first started collaborating and having a group of students come out. Next slide. So on our programs, students get really hands-on work experience, and that's both unique with this Virginia Tech program because of master research, but it's also a way for students, as Sarah, you and Adriana and Lucy talked about their experience in the beginning, it's a way for you to be fully immersed in the field. So we really like to take the classroom outside of the classroom and into the world. So you get to have interdisciplinary workshops, and you can expect workshops on environmental and community-centered design, research, and really what our focus is on is the implementation of projects. We want students to get into the field and implement change. Next slide. Here are some projects from 2025. Each of our university programs that comes down to Ecuador, we partner with about 15 different universities per year, and each one builds a project. And so there is very much a design portion where you learn about bamboo design and architecture, and then you have theory workshops and lessons, and then you go out into the work site and you build from scratch a project. A lot of our projects are for community infrastructure, bus stops, pavilions at schools. The center photo in the middle bottom is a pilot house we built last year in the Amazon region using not mass blue panels, but a similar type of panel called CBFT, or cement bamboo frame technology, and it's another way of trying to mass produce bamboo into a system, into a unit, and then be able to ship it and put up a house much faster. And so that was a pilot house project. Next slide. So here's the summer program details. So I don't know if you guys can have a QR code to scan, but if you're interested in participating in this program this summer in Ecuador, we'll be going to the Amazon rainforest. It's a city called Tena. There's a university there called Iquiam University. The dates are May 16th through the 25th. So it's after spring semester ends, before summer internships usually start, so plenty of time to get back home to summer internships. We generally have like a 15 student minimum, but can go up to 30 students. And the cost of the program is $2,290, and that does not include insurance or airfare. So roughly, approximate cost could be anywhere from $3,000 to $3,500, which for the 10 days immersive experience with hands-on work and implementing projects and getting a lot of learning in, it's a great value in terms of study abroad options, especially if you're having trouble fitting in study abroad to your schedule or what your summers allow. Some important dates, so there is a first deposit that's due with registration. You register via our website, so if you scan that QR code, you'll get an email that have all the links and information. You'll be invited to our next info meeting. But yeah, we can go to the next slide. So a little bit more about what to expect. So here's some pictures of this is the Rinder of APL University. It's a really beautiful campus and represents, it's a public university in Ecuador that sits at the edge of the Amazon rainforest. And so all of the professors and research and labs at IPIAM, they all have a focus on how to solve ecological climate challenges that the Amazon is facing. So, instead of just an architecture department, they have a sustainable architecture department. Instead of just an agriculture department, they have the agroecology department. And the research that they're doing is all integrated into communities, local communities, local indigenous communities, and has a real impact in those communities. And so it's a really perfect place for us to be studying mass food. As you guys have heard how mass food can change the landscape of housing. Currently in the Amazon, people build houses out of cinder blocks, and they have to, bring those cinder blocks from mass-produced in cities, down rivers, lots of hours. And actually the Amazon is a very abundant place to find bamboo. So if there was the ability to create a more modern bamboo housing option, people would have readily available resources. So on this program, you're going to explore bamboo construction and innovation and design and how it really pertains to the housing crisis. Not just the Amazon housing crisis, but also the housing crisis in the global south. You'll get hands-on bamboo construction work experience. As Adriana or Sarah you mentioned, you get AXP hours, and you get to do be hands-on with the mass food research as well. You'll learn alongside Ecuadorian architects, engineers, builders, community members, and students, and be immersed both in the project work as well as in the beauty of the Amazon rainforest. We'll do tours to the Amazon and learn about bamboo harvesting from local women-led cooperatives. And you'll also get to learn about the realities of the housing and climate crisis, and what kind of challenges the Amazon region is facing and how could these solutions solve those. And so yeah, if you're interested in our program, please sign up. Please get in touch with Adriana, Sarah, you, Lucy for more information about their experiences. Sarah, you and a team of students are leading the effort this year, and so if you haven't had a chance to get in touch with them, let us know, and we'll hope to see you in Ecuador this summer. Thanks, Jonas.
Thanks a lot, Beth. So I'm just going to go through a couple more slides about other opportunities on campus. So Dr. Heineman, in his lab and in collaboration with our lab, offers several courses, BIM wood course, green building, and so on. And then he also has research projects, some with bamboo and others with wood, even with some wool. So if you're interested, you can contact him directly or me, and I can connect you. Really great opportunities if you really want to see how things break and fail. That science is really fascinating and something he can help contribute to your education. Also, Ramtin is here. I saw him, but now I lost him again. He's often teaching this ICDF class. I hope that he does bamboo again soon. I'm not sure if he feels the same way or not, because it is really challenging. But they did a really beautiful project, and we still have enough bamboo from the Upjohn Prize to do one more big project like that. So hopefully in the next couple years, we'll see another interesting project using bamboo and digital fabrication. And then finally, I offer a course, not every year, and I'm on sabbatical next fall, so I might not next year, but in general, I offer a course at least once every year and a half. That's a hands-on course with bamboo. Sometimes we're making the tools that we make the panels with. Other times we're making projects. There were two structures before the yellow one that Ramtin ran that were that were run under my direct direction, a red one and a blue one. The red one is in the lobby now. And I expect we'll do more of these kinds of projects in the years to come. Also, a good way to get involved is the ID minor or courses with Brooke Kennedy in biomaterials. Also, if you decide to go to graduate school, I'm always looking for students interested in the intersection of architecture, industrial design, and biomaterials. So hopefully that's helpful. And then I'll leave this slide up. This gives a link to both the RFI site and also to the Biodesign Research Group, and just open it for questions. And why don't you guys come back up for a question and answer if there are any. So please feel free to ask questions now. Yep.
Thanks for sharing your work. During the presentation, I noticed that sometimes the bamboo is inspiring the design, but sometimes the bamboo is adapting to the design. So I wanted you to talk a little bit about this and what was the most inspiring part of the bamboo that changed how you think about architecture, geometry, or even construction.
So actually, I'll answer it too, but do any of you want to answer that question too?
Yeah, I can talk about it a little bit. So with the designs I was working on for the multifamily housing, the aim was really to create an alternative to concrete block construction. So they kind of, what Jonas and Lucas were asking for was a design that didn't look like bamboo. So that was kind of a challenge because I think it's beautiful, but they were saying that in Ecuador, a lot of the people there don't really like they look down on it because it's kind of like a poor man's material. Like if you have money, then you use concrete. So they were trying to kind of make the bamboo design look like concrete or like in that field. And then I think with some of the bamboo structures you see, I think when RFI is building those, they really do want to celebrate bamboo as a material. So yeah, it was an interesting relationship.
Anybody else?
I'm not sure what the question was, Jonas, but I was just going to add that it's partially it's not necessarily the aesthetics of concrete, but the stealability. So like when you're in the tropics, being able to be in an air-conditioned, bug-free room is like the ideal. And so stick frame bamboo construction being round, although it's beautiful, we like it a lot, it's really great for open air structures, and that is not bugless or air conditioned sealed.
So just to answer it more broadly too, so we began the research looking a lot at the morphology of the bamboo, and that's still very much part of the work. So in other words, just following the taper, making something flat but tapered is not something that comes to one's mind right away. So on a very technical level, we're very kind of in touch with the bamboo's form and shape. Also, early in the research, we got a container full of bamboo from Vietnam, and in containers when they ship over the ocean, depending on the time of year, it literally rains in the container. So we opened the container, I opened the container, and saw spider webs of mold everywhere. And it was really, really terrifying, both like the risk of health, but also this huge, $30,000 investment in research. And I thought, oh my God, it's ruined. So I called Susan Lucas, who runs a bamboo organization, and said, oh my God, but she's like, relax, it's always like this, don't worry. So we wound up having to clean every piece of bamboo. We could have brought it into the lab moldy. It wasn't the kind of mold that would be particularly harmful, but it wound up being a really amazing opportunity to touch every piece of bamboo. So every student for the first 4 years of the research had to clean about 30, 40 pieces of bamboo before they came in the lab, before they did anything else. And so we all sort of got to know the material through an intuition in a haptic way that we never would have otherwise. And during that same time is when we were making these really kind of complex structures. I didn't get into this because the retooling project is not the goal of the lecture today, but basically the thing we were really exploring there in part was how many variables of unit, of measure, of repeatability, of computation can co-occur with a biomaterial if you celebrate it for its kind of normal qualities. So one is its variation. So we started, at least in the last structure, to use nodes of measure instead of feet, inches, or millimeters. So in other words, a part would end at a node and begin at a node, and we would use a library to kind of determine that. So in these ways, we've become very interested in those aspects of the material, but it's always a kind of compromise. And my critique of bamboo, why bamboo has been slow to really do much more for the built environment, is because so much of the energy is going into formalism. There's really beautiful work that Ibuku, who's an artist-run architecture firm in Bali, with Neil Thomas, an engineer, have done really, really beautiful structures, award-winning structures, but they don't really move the needle of sustainability, right? They help our imagination, but then what's the next step? And so even though it may seem banal, that's the step I'm really interested in, is how do we really get bamboo and other biomaterials into more structures? Are there any other questions? We probably have enough time for like one or two more. Yeah.
I have two questions. Pick between them. Warriors of both. I'm wondering if you've thought about fire control and fire safety with respect to bamboo construction, especially as you move from single-family, sort of lower risk, low-rise buildings to higher risk, multi-family, multi-story structures.
Yeah.
And then the second, and you may have addressed this and I just sort of missed it, but in your early slides you talked about a continuum of sort of minimally processing the bamboo and then sort of maximally processing it and making it look more like an engineered CLT panel. Why is it that we don't see more of the adoption of this sort of more processed bamboo?
So actually, we'll answer that question second, and Lucas can actually answer that one. Lucas, I'm going to repeat it now, but then I'll answer the first question. The question was, like, why is it that we don't see more engineered bamboo like CLT in the built environment? And we'll talk about that second. So the first question, remind me of it again now. Yes. So so a couple things. One is, the reason why we're doing floor by floor framing is to not create these chimneys. Also, the reason, I didn't say it very explicitly, but the reason why we need stucco, it's not just to seal the thing up for bugs and sun and water, it's also to seal it up from risk of fire. So we think that the strategy will be a mineral-based solution to reduce the risk of fire.
Do you have plans to formally test it?
Absolutely, yeah. But we don't have budget for it yet. But we will definitely, and we'll test it based on, probably on each country's requirements. And that's the other thing I should mention is I don't really see, we're working with Princeton University right now, and they want to explore the U.S. market as a platform for the system, and I'm encouraged to do it because it brings like visibility to the research and more people thinking about it. But I really believe that we should leave these materials where they are and where they come from and use them in context. And so in each of these countries, whether it's seismic or typhoon or fire, there's not only like the scientific questions, but how do we slow down fire? There's also how do we program the building differently? Because actually in most of these countries, because they've built biogenic buildings of once or another for a really long time, they typically put bathrooms, but especially kitchens, even before they were using cement for everything, in a masonry system. So the kitchen was not in the wood or bamboo house, it was an annex connected by a corridor in order to protect the risk of fire from the rest of the structure. So these are also strategies that have been talked about a little bit in some of the work we've done already, but that we'll continue to explore, as well as just simply fireproofing strategies. Also, we did some work on campus in the dorms, and we had to have that material fire rated. So there are chemical solutions, but I think most of them are phthalogenated solutions that are definitely harmful for humans and for the environment. So these are ongoing questions that we'll have to ask as we get closer to making buildings. So Lucas, if you would just talk a little bit about your experiences, just for a minute or two, with BAMCore and your other experiences, and where you think the challenges are for why bamboo isn't industrializing as an engineered material in North America especially, but worldwide.
Yeah, so in addition to my work at RFI, I've been working in the capacity of supply chain director for over the past about 5 or 6 years, we're two of the leading North American companies making engineered bamboo products. One of them was making a nail laminated timber, a structural decking product, and the other one was making, just Bamcor, went out of business recently, was making a 1.25 inch thick panel that it's like a prefabricated framing system for residential construction market mostly. All those products relied as the sort of building block element, the raw material format they used is the bamboo slat, which Jonas is showing there up on the screen right now. It's like a rectangle that is extracted out of the wall of the bamboo pole. So obviously the bamboo has curvature, and so to take a rectanguloid out of a curved shape, you have to lose a lot of material that needs to come out of the center of the wall. And so like it shows in the one that says 6M there on the left, you can see that the little shapes in the center are the actual slats that the bamboo yields, and then all of the white around it is just basically solids that needs to be stripped and planed away to get down to that rectangular shape. And by the time you do that, it's only the first couple sections of bamboo that have a thick enough wall to extract that slat out of them. And then even the pieces that do have a thick enough wall, you have to plane away so much of the fiber that what you end up with is less than 20% of the fiber of any given bamboo that gets into an engineered element. So back to your question of why isn't there more structural engineered products made out of bamboo? You know, strength to weight ratio is there, the material is abundant, it's renewable, it's low cost in the field, but by the time you create the slat and then reconfigure that slat into a panel or a beam, it's like a tiny little piece, right? So to make a big old beam like a CLT, you might need hundreds of them. And then so edge gluing hundreds of little tiny pieces back together to make a big structural element is tedious and expensive work, requiring a lot of glue. And then meanwhile, you haven't paid the farmer very well for the bamboo because you're only really needing 20% of what they're giving you. And so it's kind of a recipe for inefficiency, which is one of the big things Bamboo solves for. It's not trying to take bamboo and make it into wood, make it into a solid rectangular structural element. It's keeping bamboo, but lightly modifying it in a way that allows it to be more versatile and uniform as we need construction materials to be.
I'll just finish with one last comment. There's also some research in thermally modifying bamboo where you take the bamboo cane, typically it's split in half, the nodes are removed, and then it's pressed, it's hot pressed flat, and the lignin in the bamboo, gets the glass transition and kind of reconfigures the bamboo into a more solid flat state. So there are some efforts to try to use bamboo in other ways to make it into a rectanguloid. And I think some of those are promising, but so far everybody who's tried has run out of money and opportunity before they really solve the problem. And so, I think that in the years to come, especially if timber becomes any more scarce, these questions become more interesting and more important. But right now there's just, there's so much competition with timber to do that anywhere that wants something like CLT that I think there's a reason why these companies are failing. Part of it's bad luck and bad timing. There's been 3 of them in the US in the last 6 years that have failed. But part of it's just that there's an incredibly entrenched wood industry that even though these products of CLT are new, the industry they're coming from is 300 years old, right? The industrial development of timber as a material is incredibly mature, and bamboo is incredibly naive right now. And it's hard to even come to the table in many ways. Is there any other question? I think we're almost out of time. We are. In fact, maybe one more and then we should call it. All right, well, thanks everybody. Thanks guys.